Okay, here are the problems on oscillations. Question number 1. A fisherman's scale stretches 3.6 centimeter when a 2.4 kilogram fish hangs from it. Oh, that should be hangs. And what is the spring stiffness constant? And what will be the amplitude and frequency of oscillations if the fish is pulled down 2.5 centimeters more and released so that it oscillates up and down? Okay, the first thing is the spring stretches 3.6 centimeters. That is delta x. And when 2.4 kilograms is hung from it, so the force created by 2.4 kilograms is 2.4 multiplied by 9.8. So you have both the force and the extension, and you can find the spring stiffness constant K. The formula is F is equal to Kx. So K is F divided by X, and F is mg, which is 2.4 times 9.8 divided by X must be in meters. That's why it's 0.036, which gives 653 Newton per meter. Remember that that's the unit of spring constant, Newton per meter. So the force has got to be in newtons and the extension has to be in meters. In the B part, what will be the amplitude if the fish is pulled down 2.5 centimeters more? So the amplitude is 2.5 centimeters. And we have to find the frequency. Frequency is 1 by time period. Again, amplitude is 2.5 centimeter. Frequency is given by the formula 1 by 2 pi square root K by M. K is 653. The mass is 2.4. And on calculation it gives 2.6 Hertz. The unit of frequency is Hertz. Remember again that frequency is 1 by time period. It's the reciprocal of time period. In the second question, a balsa wood block, mass 55 grams, floats on a lake, bobbing up and down at a frequency of 3 Hertz. What is the value of the effective spring constant? Although this is not an actual spring, it behaves like a spring and therefore it has a spring constant. The mass is given and the frequency is given, as in the last question. The formula for frequency is 1 by 2 pi square root K by the mass. Now, square both sides so that we get rid of the square root. So that gives F squared is 1 by 4 pi squared K by M, rearranged to make K the subject, because all of this will go onto the left side into the numerator. And 55 grams has to be changed into kilograms by dividing by 1000. And then the frequency is given. So it's 4 pi squared mass multiplied by the square of the frequency, which gives 19.54 Newton per meter. In the B part, a partially filled water bottle of mass 0.25 kilogram and almost the same size and shape of the balsa wood is tossed into the water. Now when it says it's almost the same size and shape, that means it has the same spring constant. And this time we have to find the frequency. Frequency is again this formula. K is 19.54 Mass is 0.25 kilogram. So that gives 1.4 hertz. In this third question, the position of simple harmonic motion as a function of time is given by x is 3.8 cos 5 pi t by 4 plus pi by 6, where t is in seconds, x is in meters. And you have to go find the period and frequency. Get x is equal to 3.8 cos. That's the given equation. And you have to compare it with the general equation, which is x is a cos omega t plus phi. Here, a is the amplitude, omega is 2 pi times the frequency, and phi is called the initial angle. Okay, omega is 2 pi times the frequency, as we have seen in circular motion, which gives frequency as omega by 2 pi. That is, from this, by comparison, you see that omega is 5 pi by 4. You see that comparison there. And that's why F is 5 pi by 4 divided by 2 pi, or 1 by 2 pi times 5 pi by 4. The pi's get cancelled, and you get 5 by 8 hertz. And time period is just 1 by frequency, gives 1.6 seconds. In the B part, you have to find the position and velocity. Now this part is not required for college physics students, so you can skip that and let me run through this part. It's calculus based, and trick based classes don't need it, so I'm going to go over that, and I'm going to say that you do not need this part unless you're taking a calculus based course. So we go to number 4. In number 4, a 1.25 kilogram mass stretches a vertical spring 0.215 meter. If the spring is stretched an additional 0.130 meter and released, how long does it take to reach the new equilibrium position again? So from the first information given, you have the mass, and you have how much it stretches, so you can find the spring constant. F is kx. Remember, F is 1.25 times 9.8, because that's force, mg. So 1.620. That is a mistake. I have, in place of 1.25, I'm using 1.62. So let me just change. It's better to change the question. Let me just change this as 1.62. That'll be the best thing. Okay, so 1.62 times 9.8 by 0.215 gives 73.84 Newton per meter. Once you get K, now the second part says the spring is stretched an additional 0.130 meter. So that's the amplitude. How long does it take to come back to the new equilibrium position? Now from the bottommost position, for it to come back, to return to the equilibrium position, how much of an oscillation is that? Surely that's not one oscillation. That is, you guessed right, that is a quarter of an oscillation. From the lowest point to the equilibrium, it's a quarter. From there it goes up again by the same amplitude, and that'll be another quarter. Okay, so what we got to do is find the time period and take 1/4 of that. Find the time period and find 1/4 of that time. Okay, time to move from maximum to equilibrium is t by 4, and t is given by 2 pi square root m by k. M is 1.62, k is 73.84. That gives 0.932 seconds, and therefore a quarter of that would be 0.932 divided by 4, which is 0.233 seconds. In the fifth question, if it takes a force of 95 Newton to compress the spring of a toy pop gun 0.175 meter in order to load a 0.160 kilogram ball, with what speed will the ball leave the gun if fired horizontally? Here you see that the force is 95 newtons and the compression is 0.175 meter. So you can find K using F is equal to Kx, and then the elastic potential energy of the spring is 1/2 Kx squared. All that potential energy gets converted into kinetic energy. So you're going to say 1/2 Kx squared is equal to 1/2 mv squared. So that's the idea. First, to find K is equal to F by X. F is 95 newtons and the X is 0.175 meter. So you get 542.9 Newton per meter. The elastic potential energy becomes equal to the kinetic energy of the ball. This is a conservation of energy. And elastic potential energy is 1/2 Kx squared. Kinetic energy is 1/2 mv squared. Vm stands for maximum. The halves get cancelled, rearrange, and take the square root. It's K by M. M is 0.160, that's the mass of the ball. And the amplitude is xm, that's 0.175, and you get 10.2 meter per second. A simple case of conservation of energy. In number 6, a mass of 240 gram oscillates on a horizontal frictionless surface at a frequency of 3 Hertz and with an amplitude of 4.5 centimeter. What is the effective spring constant and how much energy is involved in this motion? Okay, the mass is given and the frequency is given. You can find the spring constant. Omega is 2 pi f, and also omega is square root k by m. Put those two equations equal to each other and you get f is equal to, actually I'm squaring both sides now, 4 pi squared f squared is equal to k by m. Remember, we have used this formula before. I'm just showing you how to get it. Make k the subject, as we had done in one of the previous problems. Mass is 0.24 because it should be in kilograms. Frequency is 3. And when you substitute all that, you get 85.27 Newton per meter. And how much energy is involved in this motion? The total energy is equal to maximum potential energy, which is 1/2, which will also be equal to maximum kinetic energy. Remember that at the amplitude position, all the energy is potential, and as it's passing through the equilibrium position, that's when it has maximum speed. So all of the potential energy becomes kinetic energy. So you could either use 1/2 kx squared maximum, which is ka squared, because the maximum value of x is the amplitude. I hope that's clear. So 1 half k a squared. K is 85.27 and the amplitude is 4.5 centimeters, but that is 0.045 meters, and you get it as 0.086 joules. Number 7, a clock's pendulum has a length of 0.9930 meter. The clock loses 26 seconds per day. How should you adjust the length of the pendulum? If the clock loses time, that means it's swinging slower, which means the length of the pendulum has increased. Something like that would happen in summer due to the expansion. So, if it loses 26 seconds per day, how would you adjust? Okay. First of all, we got to look at how many oscillations are there in a day. And also remember that any clock, a pendulum clock, makes one oscillation in 2 seconds. That is a fact that you have to know. Any pendulum clock makes one oscillation in 2 seconds. That means it takes 1 second for each swing. Therefore, 2 seconds for one oscillation. So the time period is 2 seconds. And now the number of seconds in a day, 24 hours times 60 times 60, because 1 minute is 60 seconds and 1 hour is 60 minutes. So that's 86,400 seconds. And therefore, how many oscillations does it make? Divide that by 2, because every oscillation takes 2 seconds, which is going to give you 43,200 oscillations. And it loses these 26 seconds in 43,200 oscillations, which means that's equivalent to like 13 oscillations, like, right? 26 seconds is equal to 13 oscillations. Therefore, the number of oscillations that actually this clock makes is 43,200 minus 13, which is 43,187. And therefore the new time period is the ratio 43,187 divided by 43,200 times the old one, which we know is 2 seconds. And that's the formula for time period of a pendulum, 2 pi square root new length by g. Okay, so the length is 0.9969 times L naught by G. Okay. I don't know from where I'm getting all these numbers. Okay. I'm using a number 0.99969 in place of what's given there. Okay, so let's assume that's 0.99969. Okay. Well, really it doesn't matter. You just need to know how to do the problem. So oh no, that was just the ratio. Now I see that. That was the ratio, 43,187 divided by 43,200. So that is the ratio. Pardon me for that. And then you have the same 0.9930. So that goes, and then you get the new length as 0.9924 meter. Just trying to work backwards and say that the old length was 0.9930 meters. So you need not do that. So try to understand this problem. I do not need the problem on damping. So let's go to this one. A 1150 kilogram automobile has springs with K 16,000 Newton per meter. One of the tires is not properly balanced. It has a little extra mass on one side compared to the other, causing the car to shake at certain speeds, which is not comfortable. Okay, it's a very uncomfortable experience. So that's why the tires have to be balanced. If the tire radius is 42 centimeter, what speed will the wheel shake the most? Okay, you have the mass of the automobile and you have a K. There are two ways and we can find it now. Shaking the most when the frequencies are matched. Okay. So shaking will be maximum when their frequencies are equal or matched. And this phenomenon is called resonance. And the formula for frequency, both of their frequencies must be the same. Frequency of the spring and the frequency of the tire. So omega is V by R in circular motion. You remember that? Linear velocity divided by radius. And in this chapter, we saw that omega is square root K by M. So put those two together, make velocity the subject, and radius goes to the other side, so that's 0.42 in meters. K divided by, okay, we need to divide this 1150 by 4 because the total mass is balanced on 4 tires. So each tire only gets 1150 divided by 4. So that is 3.1 meter per second. Well, I'm just writing down. Each tire supports 1/4 of the mass. So when the car is moving at that velocity, when the tires are spinning at that velocity, rather, the shaking will be a maximum. You don't need this question. This one, at what displacement from the equilibrium position is the speed of simple harmonic motion half the maximum value? Let's skip that. Okay, and go to this. A diving board oscillates with simple harmonic motion of frequency to 2.5 Hertz. What is the maximum amplitude with which the end of the board can oscillate in order that the pebble placed there does not lose contact with the board during oscillation? Very interesting question. You know that a diving board is supported at one end and it's free at the other end where the person stands, and this diving board oscillates with a frequency of 2.5 Hertz. What is the maximum amplitude with which it can oscillate so that a pebble placed there does not lose contact with the board during the oscillation? It would lose contact with the board at the highest point of its oscillation as it is tending to go down, because if it goes down really fast, then the pebble will lose contact with the diving board. Okay, first of all, from the frequency given, alright, let me write that. The pebble loses contact if the board's downward acceleration, well, how would it compare with the acceleration due to gravity? Which point? At the highest point, as I told you, board's downward acceleration at the highest point is greater than acceleration due to gravity. That is when it will lose. And acceleration is given by the formula omega squared x. Omega is 2 pi f. And maximum acceleration is omega squared a. 4 pi squared f squared a squared. Because x max is amplitude. So 4 pi squared f squared a. is equal to G. And from there you get amplitude as G by 4 pi squared F squared, which is, when you calculate, substitute and calculate 4 times 10 to the negative 2 meter, which is 4 centimeter. Okay. I guess these problems will be enough, and just try to understand each one and prepare for the exam using this.